Okay, for purposes that'll soon become clear, or if you're reviewing for purposes that are already clear, we want to talk about doubling x values. So we have an x-axis here with the origin, that is the x equals 0 point here. And we're not going to numerically identify any of the other points because that comes later and it would defeat our purpose to do it now. So we start with x, well, the origin is at x equals 0. Okay, we're going to start with some x value. So let's just take a small x value here. Okay, now we want to find the point on the axis that doubles that x value. We don't know what this number is. It doesn't matter. We're doing this geometrically. So how would we double the value of x? And where would the point be for which the value of x doubles? Well, it would be twice as far from the origin. So that's going to occur here. Assuming this distance is equal to this, I think I shortchanged it a little bit, and that's something we got to fix by practice, and nobody's ever going to get really, really good at it. I won't say nobody, some people probably can. Now, we want to double that x value. So we're going to successively double x values. So how do we double this x value? You might think about that before you watch me do it, but I'd say, okay, well, if that distance is this, then this distance should be this, so that an x value about here should be about double the x value here. Well, then what do we want to do? We want to double this x value. So I should entitle this successively doubling x values. And that U doesn't look much like a U. Okay, well. Okay, we want to double this x value. Where's that going to put us? Eyeball it. Where do you think I'm going to go? I think it's going to be about here. When I look at this point is about as close to this one as this is to this one. That's not a bad way to look at doubling, although you'd be subject to optical illusions. Let's see how I did. I didn't do too badly. Okay, so now what? We want to double that x value. So let's find a point out here that's as close to this point as this point is to the origin. So let's see if I'm here. Am I closer to this point or this point? I think I'm pretty good there. Okay. Again, I can kind of test that. Let's see. It's getting a little bit big to measure with my hand. Looks like I might have put this one a little too far to the right, but that's the idea. Okay. So we're doubling our x values. Now, that's going to be an important thing. There's another related thing that we want to do with y values. Okay, now we want to change y by a constant factor. And let's look back at what we did with x. We doubled x every time. And of course the x values got further and further apart. We changed x each time by a factor of 2. Or each new x value is 200% of the old. Okay? So when we doubled x values, we changed x by a factor 2. So I'm going to write up here. We changed x by factor 2 at every step. Okay, well, let's change y by some factor. Let's change y by factor 3. So, for example, we change y by factor 3. So we can just start with some small value of y. And now we want to find another y that's 3 times further from the origin. Well, one way to do that is just kind of use our fingers. That looks like it's about 3 times as far. If we cut this in half, do we have equal segments? If we cut the distance between this y and this y in half, that should have, the distance there should be equal to the distance down here. So we can kind of eyeball that and see if we're doing that right. Okay, well, if we want to do that again, we go 1, 2, 3, maybe here. Now if we cut that in half, we get this distance, and it's about equal to this distance. So I think we did that fairly well. Okay, now if we want to change this by factor 3, well, that's actually going to take us off the end of the graph. We could go back toward the origin to get another point if we wanted to. We could take a point 3 times as close to the origin as this one. We have just enough. That chalk line is a little thick. That didn't really come out well, but it would be possible to do that if you had a good sharp pencil or something. So that's what we mean by changing y by a constant factor. Now, there's another way we could have done that, and another way we could have done this. So let me just illustrate that real quickly. And let me back up just a second before I do that and comment that, okay, if this distance is 100, then what's this distance? You should look at this distance and say, well, if this is 100, that's got to be about 300. If this is 100, then this has to be about 300. Okay? That's another way of looking at changing y by a constant factor of 3. This is 300% of this. This is 300% of this. That whole vocabulary. The ratio of this length to this length is 3. The ratio of this length to this length is 3. And if you've developed a little skill in estimating, that's a very good way to do this sort of thing. Okay, now the other way, we could have done the x-axis. Here we have the x-axis, and here we have the origin. We could have started out here. Now, we don't want to double this value because that takes us off the end of the board. And if we keep doubling, pretty soon we're going to be out in the parking lot. But if this is x equals 0, so this is our first x value, how do we achieve a sequence of points where x doubles? Well, that's easy to do. We just cut x in half. Then from here to here, it looks like x doubles. Now, when I look at that on the screen, it looks like I put that in somewhat too close to the origin. So let me just kind of fix that just a little bit. Okay, so I think maybe here is going to be better. If I get out here and look at it, I can see it better, but then I block the board. And I haven't yet adapted to being able to judge that from this angle. Okay, well, if I go here, how's this? Now, if I look at the monitor over here, I can see, okay, that's pretty good. Okay, cutting this x in half. Cutting this x in half, well, okay, about there. Cutting this x in half, I think maybe I get that about there, and I can cut that in half. Went a little too far. Cut that in half. Well, I'm not doing a good job of cutting them in half at this point. A little bit unpredictable exactly where the chalk mark is going to go. Okay, so, but I can get a whole sequence of x values, each of which approximately doubles the one before it. So, to say that this distance is 200% of this distance, of course, is the same as saying that this distance is 50% of this distance. Again, if you can estimate percents, estimate proportions to some extent, you can do a good job of doing this. And it gets more important when you try to do the y ratio, which might be any number. The x ratio, as we're going to use it, is always going to be 2, or if you come backwards, 1/2. The y ratio can be anything. Now, if I want a y ratio to be 3, well, I can start out here, and then I can take a point that's about, well, 3 times as close to the origin. So let's see, if that was this, then we'd have this and this, maybe a little higher. So, is it reasonable? If this represents 100, does this represent 300? Is this 3 times as great as this? I made it a little too high, but okay. And then I want to cut that in thirds. So let me just eyeball that. Pretend this is 100. I want 30. 33 1/3, but I'm not going to get it that close. Okay, about there, and then here, about here. There are many ways to think about the estimate, but by subdividing, we can pick how far out along the axis we're going to go before we stop. One disadvantage of what I did here, I chose this distance, and it was a little unpredictable where I was going to be after 3 steps. And it turns out that after 3 steps, I'm going to be up off of the axis that I drew. If I choose my point on the axis and then go 3 times as close each time, I achieve the same thing, but with a point here that might be more appropriate to my purposes. And of course, the y factor is not always bigger than 1. As we saw in previous examples, we could change y by a factor of 0.3 or a factor of 1/3. So this would be a plausible 1/3 here, where we would actually start with this point, and our second point would be here, 3rd, 4th. Whereas if we're tripling, then we'd have to, if we're tripling as we go up, then we have to start here and move out this way. Either way, we can start at this point and divide the distances by 3. And that could either represent a tripling starting here to here to here to here, or a factor of 1/3 starting here and going down to here to here to here. Okay, well, not sure you see the relevance of that at this point. So what happens if I do a tripling of my y values and cut my x values in half? I'm going to try to do that halfway accurately, so excuse me for blocking the board, but this won't take long. Okay? Okay, now, if I match up my y points with my x points, and let's just start by matching the furthest point with the furthest point, then I'd match this point with this point, this point with this point, and this point with this point here. Okay, so if I match this point and this point, that gives me a point that lies about here. Match this point with this point, gives me a point that lies about here. This point with this point. And remember, I'm not seeing this very well, so if these points, see that point, when I look at the monitor, I put it too far to the left. When I'm looking at it from here, though, I look like I have a good right angle there. So let me just kind of correct that. This point and this point, let's try to compensate for the fact that I want to put it too far to the left. It's this point pretty well above this one. It's still too far to the left. But, okay. Now, elsewhere we give the argument, if I keep cutting the x values in half and the y values in a third, my points are going to approach 0, 0. So I'm going to include 0, 0 on this graph. Then I'm going to sketch a smooth curve, and kind of screwed up here. I didn't keep curving like I should have. But we get the idea of how this graph represents a tripling of y whenever x doubles. So I can say y triples when x doubles. And if we accept the convention that we're always going to let x double, we're always going to do the x-axis with a doubling and then use various ratios on the y-axis, we could call this the tripling graph. Okay. Now we'll see how this sort of construction gives rise to what we call the power functions. And we'll talk some about the algebraic representation of power functions and how we could do calculations with these functions. But even more importantly, we want to talk about how certain power functions give us graphs that can represent observations that we can actually make in the real world. And I'll even make a bigger statement. Whenever y changes by some constant factor when x doubles, our graph represents one of these, a power function. And there's even another statement that can be made that kind of gives us the overall picture of where we're going, even if we don't know all the details at this point. A converse of this statement is this, that the graph of any power function has this characteristic, so that this characteristic completely defines the power functions. I can go even a bit further or just play off of this and say we could construct a factor 3.5 graph. Or factor 0.7 graph. Factor 3.5 graph, everyone increases by 3.5. Factor 0.7, well, y values get closer to 0 by factor 3.7.